Hello, everyone. Today I will talk about my paper on TMLR 2022. The title is Multi-Agent of Policy TDC with Near-Optimal Sample and Communication Complexities. My name is Ziyi Chen. I am the first author, also a PhD student from ECE department at the University of Utah. We studied the multi-agent reinforcement learning setting, which is basically very similar to single-agent reinforcement learning, except that, as we shown in the top graph, each agent M has its own action, ATM, and also its own reward, RTM. And these agents have the goal to find out the optimal joint policy pi that maximizes the following value function, while in the red part, we use the agent's average reward. This multi-agent reinforcement learning has broad applications, including traffic signal control, dynamic web service composition problem, stock market, etc. A very important problem for multi-agent reinforcement learning is the of-policy evaluation problem, which is defined on the top. Here we have historical data of the state ST actions, ATM, rewards, RTM. This historical data is obtained from the behavioral policy pi b, but our goal is to evaluate the value function of the target policy pi. So the target policy pi and the behavioral policy pi b, usually they are different. Why? Because in many applications, as we shown below, in these applications, it's very hard to get new samples from the target policy pi. For example, in the recommender system, if we want to apply the new recommender algorithm pi into practice to obtain the samples, then it costs much time. And if pi is not a good recommender algorithm, then some users will be disappointed, which is not good for business. Therefore, in this case, we prefer to use historical data that is obtained from the old recommender system pi b. Also, in applications such as precision medicine and the game of Go, we also don't want to obtain new samples from pi since that's costly. Now we will talk about the TDC algorithm, which is widely used for of-policy evaluation. Now we first see the single agent TDC for single agent problem, which is simpler. Usually we use the linear function approximation for the value function v pi. Here the theta is the linear parameter we want to compute. So to compute theta, we can use the update rule of TDC as follows. Well, in the red part, we define rho I as the ratio of the target policy pi and the behavior policy pi b at the ith sample. This is called the importance sampling ratio, which is very important for of-policy evaluation. So we extend the centralized TDC algorithm to the decentralized TDC algorithm into the multi-agent reinforcement learning. So for every mth agent, it has its own local importance sampling ratio, which is also defined as the ratio of its own target policy pi m and behavioral policy pi bm associated with the mth agent. Then we want to compute the global importance sampling ratio, which is defined as the product of all the local importance sampling ratio. However, this involves a key challenge that the rho I involves all the agents' sensitive information, that is their behavioral and the target policies. So to protect this sensitive information, we propose our novel solution that we rewrite the rho I into the exponential of the log rho I m. Here, in the red part, the agent's average of the log rho I m can be approximated by the following local averaging steps, which is also known as the gossip as shown in the blue. And it's well known that such gossip updates converges exponentially fast to the true value of rho I. Then with the approximated rho I as rho I hat m, we propose our own decentralized TDC update for the multi-agent case. Here, the yellow part is the local average, also gossip of the parameters, which is very important for decentralized optimization. And we propose two novel designs. The first novel design is shown in blue, which is to approximate the important sampling ratio rho I, as we have introduced in the previous slide. Our second novel design is the red part, which is the mini batch of size n. This helps to reduce the gradient variance by 1/n, and also reduce the communication frequency and the complexity, since we only need to communicate the parameters after collecting every n samples, instead of only after every one sample. We compare our algorithm with the existing decentralized TDC algorithms. The existing decentralized TDC algorithms focuses on simplified settings such as independent MDPs among the agents, while our decentralized TDC focuses on the very general multi-agent reinforcement learning settings. Our second advantage is that existing decentralized TDC algorithms need to share the agent's policies, which is sensitive information, but our algorithm will protect those sensitive information. And our third advantage is that existing decentralized TDC algorithms use either IID samples or finite sample size to analyze the convergence property, while our decentralized TDC used Markovian samples, and we can use as many samples as needed. We also compare our complexity with the complexity of similar algorithms. This is our sample complexity. In the first item, this is our sample complexity. This one matches that of the centralized TDC algorithm for single agent case. And also our algorithm is near optimal in the sample complexity in terms of epsilon, since the theoretical lower bound is epsilon to the power of -1, and our sample complexity is only up to logarithm to that. And then for the second one, we compare the communication complexity for the linear parameter theta, which is what we finally want to compute. We remember that theta is the linear parameter for approximating the value function. And for this one, we compare with the existing decentralized TD algorithm, which can only be used for own policy evaluation, which is simpler than the of policy evaluation. We see that although our algorithm focuses on the of policy evaluation, which is more difficult than the on policy evaluation, our communication complexity for theta is much smaller than that of the decentralized TD. And also our communication complexity is proportional to the log epsilon to the power of -1, which is optimal for decentralized strongly convex minimization. And for the third part, we show our communication complexity for importance sampling ratio rho. Since this is the first finite time complexity result for decentralized TDC, so the communication complexity for rho, we don't have any other algorithm to compare with. This is our simulation experiment. For the first simulation experiment, we compare our decentralized TDC with the existing decentralized TD0 algorithm, which only has batch size 1. And that's for own policy optimization, and we sort of that the decentralized TD0 is for own policy evaluation, and we adjust that to of policy evaluation by multiplying the importance sampling ratio. And we found that our decentralized TDC algorithm have a very similar sample complexity to that of the decentralized TD0 algorithm, as shown in the left figure. But in the right figure, we show that our decentralized TDC algorithm converges faster, and the convergence becomes faster with increasing batch size n. So the n really helps to reduce the communication complexity, but the sample complexity almost remain the same. Then we see the effect of the communication rounds AL for the importance sampling ratio rho. We see that as the communication rounds AL increases in our algorithm converges faster in terms of the number of communication rounds. So with increasing AL, the communication complexity also decreases for both the fully connected network as shown in the left figure, and also for the ring network as shown in the right figure. Then our second experiment is for the real application called two-agent cliff navigation problem. We did a similar comparison with the decentralized TD0 algorithm in terms of various batch size n, and we found that as the batch size n increases, the sample complexity on the left almost remain the same, but the communication complexity is much reduced. This is also the same as in the simulation experiment we talked about just now. For the third experiment, which is on the application of path finding problem, the result is similar. Thank you.